So today we have two speakers. We have Dr. Robert Panoff and Dr. Kelly Roos. They're going to speak about their use of computational methods in physics. This is the second of our physics-related presentations. And by the way, if you missed the first one, that is posted on YouTube now, and you can find it by going to the SIG-HPC Education website, which is sighpceducation.acm.org. Today's work will also be recorded and posted sometime in the next few days. So to begin, I'd like to ask Dr. Panoff to start with his presentation. So Bob, would you go ahead?
Okay, I'm going to try to share my screen. Are you able to see that there?
Yes, go ahead.
Okay, I'm going to see if I can. I'll hide the thumbnail videos. So what I want to talk about a little bit is the experiences that I've had working with small to medium-sized colleges and also community colleges, and talk about a basic motivation for including computation even at the intro level or the gen ed, not waiting for quantum 2 or for classical mechanics, but part of the attractiveness of computational thinking will help us attract and retain students in physics and science, and also students being exposed to what computation can do. So for instance, next semester I'm teaching a class at Wofford College called Scientific Investigations Through Computation. And we're going to do chemistry, physics, biology, economics, but all of them are going to be analogical to one another, with the driving examples from physics being things that students can literally get their hands on. So the idea of having a dynamic, visual, and interactive context in which to explore content and algorithms is important. A second motivation for what we're doing is this idea of modeling first. We have a lot of people who think that computation in physics is to teach programming and coding, but I believe that computation can be accomplished through a variety of modeling environments that lead to coding, but if you start with coding, you lose a lot of people early on and they get discouraged. So for today, I'm only going to use, well, I shouldn't say only, I'm primarily going to use Excel as my modeling environment to show you that you can do dynamic, visual, and interactive explorations and get some good understanding of things before you move into Python or Mathematica or Java or Fortran or high performance Fortran. I'm going to stay away from the massively parallel computing work that we also do, because I really want to get more computation into gen ed courses and into introductory physics courses. So the way this is going to work is, if you want to do it yourself, each of these three links is an Excel spreadsheet that you can download. And in so doing, you know, you can figure out what you have there.
Let me just remind people that the link to this presentation is in the chat window if they want to follow along.
Oh, yes, good point. And because I made a typo when I emailed out the link is presented in the chat window under both its correct and incorrect spellings. So the first thing I want to do is just show you a couple of parts of what we do at Introductory Computational Thinking, which involves understanding round-off truncation and resolution so that students understand what computers can do and what they can't do, what's expected and what's not expected. So here's a simple calculation of typically done 3, 6 minus 1, 6 minus 1, 6 minus 1, 6. So if you say, what do you expect to get? Students say, well, you would expect to get 0. And if you do the calculation in Excel, it says it's 0. But then you go back and ask yourself, if 1/6 is actually not 1/6, how is it possible that exactly 1/2 minus 3/6 gives you 0? And the answer is it really doesn't. Excel is lying to you. If you put parentheses around the calculation, that's shorthand for don't lie to me. And what you see is the expected round off error that you get. But what's unexpected is that Excel tells you that 1/6 is rounded up, but instead of getting exactly 1/2 minus more than a sixth minus more than a sixth minus more than a sixth, it gives you a positive number. And that's because this number is actually not represented in memory with a 7 there. It's actually truncated, not rounded. So that's one of the, but again, to see it without having to write a program to understand what's doing, you can just type it in. For resolution, when we think about well, we have a whole series of exercises called the look and feel of 0. If you start with Avogadro's number and ask yourself, if I add 100 million to Avogadro's number, what do you get? And the answer is no change, because 100 million compared to Avogadro's number is, it looks and feels like 0. It's the additive identity. If I come over here, let me get back here. If I come over here and make it 500 million, I get no change. If I make it 600 million, okay, now that number can be distinguished from 0. But we have a series of simple exercises that don't require teaching programming first, where all they need to do is the Excel. And what we found in a lot of small colleges is that the students are expected to graduate with some ability of using the Microsoft Office suite, what they call the productivity suite on some campuses. So using Excel to teach the lessons of numerics isn't such a bad idea after all. So that's just one simple example. The standard introductory physics is essentially solving a dynamical problem, sort of a falling rock on a spring with drag, and sort of looking at that example again. The way I've been doing it is to kind of set up the problem once and explain what's going on with this paradigm of what you have is what you had plus what changed. Where you are is where you were plus how far you moved. How fast you're going is how fast you were going plus how much you accelerated. And if you have essentially the definition that the acceleration is the change of velocity over change in time, then when you get to the equations here, then in each case, you have something that you can use to kind of go through the process. Now, what I'm doing to make this work is I'm using the ability of taking any cell and changing its, or giving it an additional name. Besides A2, this cell is now called gravity. This is delta T. This is V0, H0. This entire column is called V new. This entire column is called X new. And so when you actually come in and look at what is the relationship, that the new value is the old value plus the change in the value, then what you have is equal to what you had plus what changed. I mean, it's the standard multiply up. So when you do that, you get a very simple Euler equation. By exact, I actually typed in the formula as if you had integrated it exactly. And it looks just like you would expect it to look using the names of the cells rather than $H, $32. We can make it very reasonable. And so that's what we're going to compare, the error being the difference between the two Euler integrations and the so-called exact polynomial answer. So if I come over here and just copy this down to give you more things. In each case, the old value is equal to the new value. So in each case here, if I looked at the value old, the first thing I do is set it equal to the previous new. And then if I just was to copy that down, you get, as we are all or most of us physicists, the expected behavior. I'm going to go back up here and change this so you can see the graph of the parabolic action where somewhere around 10 seconds, dropping a ball at a certain height, you reach the ground. You see that integrating a constant acceleration gives you a linear velocity. And you see that as time progresses, you get a larger and larger error. So the first thing that I know a lot of you have done, and I know I've done it, is we teach this Leapfrog method. But the wow factor of the Leapfrog method is I want you to watch the error column where I add a /2 so that only the very first time I calculate the velocity, what I'm really doing is I'm now going to be calculating the velocities on the half step and the positions on the full step. And watch what happens to the error if you do that. Now, if I was doing this in a classroom, normally I ask the students to be very quiet while I do this, but they can't help by saying, ooh, or ah, or oh, look at that. Because you can get this basically a second order effect by doing a higher order integration by doing that. Now, if I go back and take that out, you could say, well, in Euler, the way you normally get a smaller error is to use a smaller step size. So if I do that, then you can see the errors are smaller, but they're still real. So I could come back over here and do the same thing and get a pretty good value. Now, the idea of doing this is there's a certain point where when you're teaching modeling, what you have the equations, you have your ability, but what you want to be able to do without having to write a lot of code is just to be able to change this once. So if I go up to my first definition of V new, the new velocity, and I subtract off a term that's proportional to the position of the particle, this is essentially, adding this resistive force. You could say, well, what's the effect of doing that? And you could say nothing because K is 0. But if I change K and give it some value, and then sort of come in here, when I come over and take that simple, let me get rid of that part there. And I copy that all the way down, you can see that by copying it down, that double click is all the work that you have to do. You now have this spring effect. And if I went back up there and took off something that was proportional to the velocity, why not call it a drag term? Because that's what we always do. And again, the drag term doesn't do anything until we change it. But if we add, oh, I have to copy that all the way down. Double clicking does that. Now you're getting your damping force coming in. And so you can see that it's dynamic, it's visual, and it's interactive. And what makes this work in the classroom is that I prepared the spreadsheet ahead of time so that the first 2 rows and the graph pointing to the columns is already set up for the students. And so I don't have to have entire lessons on teaching Excel. Most of them know the bare minimum that they need to get through the thing. But it makes it very realistic for the students. You can see that the position and the velocity are out of phase. You can see the effect of these things going on. And if you're a developer, you could even add a scroll bar and make these things even more dynamic. And then let's change this link to then I'm going to make this a 30 over 100. Right. So now I have no drag, but do you see that as I increase the amount of drag, and that ability to do it without a lot of programming, you can just use the ability of the code itself to do that, I think is rather compelling for what we do. So we can cover a lot of physics, and we don't necessarily require the students to do a lot of programming before we do that. But what we can do is add the stuff in as it's going and give them the ability of grabbing the model and varying it in time and seeing the effect of that. The last example I'll use has to do with iteration. And one of the things that we do a lot in physics is solve certain problems iteratively. And a lot of people are not aware that within Excel, there are preferences that allow you to make the calculation manual and have it iterate rather than making it automatic. And by doing that in the preferences, it's effectively turning off the whining where, again, Excel is going to lie to you and say it can't do anything. So this is a typical example where what you want to do is to solve a problem where everybody is going to use the average of your neighbors. And the goal of the physicist is to get the calculation done exactly right once. And there you see the average of 4 nothings is 0, not unexpected. But I'm going to also introduce the idea of color as a variable. And I'm going to have a range of values that go between 0 and 40. And because I've done this before, I'm going to do it logarithmically. And I'm going to use very low temperatures to be represented by blue and high temperatures to be represented by red. So I hope it doesn't surprise you that if 0 is represented by blue, then again, getting it right once, I can copy it over and copy it down. And now I'm going to put the standard physics problem. If I take a slab of metal in contact with a temperature bath held at 40, what is the asymptotic, what is the long-range distribution of heat within this slab of metal? And if everybody is simply the average of your neighbors, then by iterating this equation, then over and over and over and over, all of those values are done at the same time. We also use this example for introducing the concept of parallel computing, because at each stage, every cell is using the previous old values, and you can see the convergence. You can also see the value of scientific visualization using color as a numeral. If you don't like the numbers themselves, you can even get rid of the numbers and just stick with the I'm going to just put, so I can suppress the printing of the numbers and I can use just the color for doing things. But what we've done, and we've done this in faculty workshops as well, is we find that a lot of the schools are telling us that what they're interested in is having more ability to focus on the content of the computation in physics, and not so much it's their job to teach programming. But what we found is that this is also analogous to something that happened in my own family back in the early 60s when Fairfax County in Virginia started teaching band in middle school. All the Panoffs wanted to be in band, but my father didn't want to rent 6 instruments. So he put a requirement that we all take 2 years of piano lessons first. thinking, of course, that would discourage us. But instead, what it did was when we started playing the instrument, my sister played the flute, I played tuba, Jimmy was Timothy, then there was a trumpet player, a French horn player, and a trombone player. We were doing something easier. We already knew the music theory. We already knew how to do scales. We could even play chords with more than one note at the same time. And now all we had to do was learn how to play that one instrument. If we're going to be doing modeling first, where we can have existing models that are already prepared for students to modify, then they can get a lot farther up the food chain. And then when they're learning programming, they already know the physics, or they know exactly what's expected of them in the computation that comes out of the physics. So we're seeing that you can do a lot. In fact, when we're teaching the programming part, we often go back to the Excel version of it first, so the students can literally see what's going to be happening. And they can see that if you get one cell correct and then copy it down and copy it over, you can actually do hundreds and hundreds of cells in parallel, but you've only typed in the equation once. Or if you're doing the falling object, you get one moment in time correct, and then as you're dragging it down, you get row by row by row. You're teaching them the concept of a loop without having to program the loop. So, I mean, what we're seeing is a lot of students say, I can do that. And then when we switch to doing population models and you're doing rabbits or rabbit populations or rabbits and wolves or other things, then we can take the analogies from physics, starting with what exists, how do they act, and then how do they interact. And those are the things that we've been able to accomplish. So we're seeing there's a lot of benefit to that, especially with students that are afraid of programming. We can get them into using computation and visualization directly. So I just wanted to show you those basic examples to give you an idea of what we've been able to do. And it's not an advertisement for Excel. There's a lot of things Excel doesn't do, but there are a lot of things that you can do and accelerate the actual use of the computer to get to the solution faster. I've used this time to solution analogy before, but the idea of getting the kids to understand what they're doing and then teach them the higher order skills of programming once they understand why they're going to be programming. So that's what I wanted to talk about this morning. Well, actually this afternoon, depending on where you are.
Yeah, thank you, Bob. So now let's open up for some questions for Bob. So you can either unmute and ask it verbally, or you can add a question to the chat window, and I'll pass it on to Bob. So questions for Bob.
I have a question. So in a class I teach to my incoming freshman physics majors, virtually none of them knows how to program in any language.
Right.
And that's, that's an argument for Excel. But then when I ask them how many people have experience with Excel, most of them raise their hand. But then when I actually get down to it and see what they can do in Excel, it's virtually nothing.
Exactly.
So, I mean, I really liked your analogy with the music and all of that. That made a lot of sense to me. But earlier, just a little bit earlier than that, you said, but everybody has experience with Excel. And so there's experience and there's experience.
Yeah,
so
it's not necessarily a good experience. I mean,
yeah.
if they had it in high school, they probably learned the way you get constants is to put dollar signs in front of columns or rows, or the way that you do. The reason you use Excel is to make a chart that you stick in a Word document. So one of the things that we've seen a benefit at Wofford, for instance, is that by using some of these examples and show them the skill of naming a cell, and show them how they can put in a slider bar, and show them what they can do for setting it up and using color as a variable, that those are sort of incremental lessons that while they're doing it, they're at least in an environment where they say, oh, I didn't know Excel could do that, or,
So that was sort of my question. So it sounds like you don't give a quick primer in how to do cool stuff with Excel. It sounds like you integrate that into the lecture on whatever it is you're doing, like whether it's the falling body or what have you. It sounds like you integrate it, or do you give them a little bit of a primer on the very first day?
Well, the primer on the first day involves the numerics lesson in which we introduce naming of cells. So if I go back to my example here, even in my naming of cells example, let me just pull that up again. This cell is given a name. I called it start. This cell is given a name. I called it step. And then I use if start, so I'm using things like names. And then if I want to vary it, I could introduce, what if I wanted to change this? And then we talk about, well, one thing you could do is you could take this number and change it, or take the number and change it, and take the number and change it. Or you can introduce a control like a slider bar that would let you, go in and do those kinds of things. So we do it in the context of a really, really simple lesson. So what they come out of it the first day is learning something about computation. I mean, we also do this that it's just true in general. I think I used the example last time where if you look up the mass of Mars, you get a value 6.39 times 10 to the 23 kilograms. That's what Google tells you. And then Google gives you the source, and the source says it's 6.4172. And then there's a source for that. And if you look that source up, it says it's 6.4185. And so, when you're talking about those are just people getting the number different. I'm not even saying it's wrong. It's just you measure Mars differently, you get a different answer. But we do things that have to do with numerics across the board and getting them used to the idea that, if they were doing Python, you would want them to take 8.5 and subtract 8.4 and explain why the answer is not 0.1, right? Because of round off or truncation. So we sort of introduce it as it's useful. Then as they use that skill, like naming a variable or using a slider bar, then we can use that for accomplishing what we want to do in physics. And then so spreadsheets become sort of enhancements that they modify, not something which, they have to build from a completely blank square spreadsheet to start with. So that's why I give them these sort of starter things where the first row is already done. Or did you notice in the diffusion, I made the cells thinner so that it looks like graph paper instead of having rectangular cells. It looks like more, so I prepared that already. And then, we can say, oh, by the way, let me show you how I did this if you're interested. But the idea is that you're kind of bringing them up the ramp without necessarily, because again, there's a lot of things in which by the time you get to graphing, you've got to teach them a lot of programming. And so it's not the best in the world, but we've used Google Sheets, we've used Excel to do these kinds of things. The reason I don't use Google Sheets as much is if I did the same thing I did here and each of you clicked on the sheet, you'd all be editing the same sheet. And if some of you were more curious than others, you'd be messing up my lesson. And so at least the Excel gives you a local copy for doing things like that. But again, it's just different strokes for different folks. In this case, I switched to programming and using other types of modeling environments later in the semester, but I want them to understand why we're doing computation in the first place, and what you can get out of it and what the power of it is. And then we get kids that are in economics and they realize that it's the same basic differential equations. The money you have on Monday is the money you had on Sunday, plus what you put in minus what you took out, right? And so it's what you have is what you had plus what changed. And then that iterative solution is really the commonality between different features.
All right, other questions for Bob? I don't see anything in the chat window. So, well, if something occurs, you will have more time at the end. So why don't we move on to Kelly and have him give his presentation. So Kelly, I'll turn it over to you.
All right, thank you, Steve. I'm going to attempt to share here, and you let me know if it works or not, all right? I think I want to share that. Let's share the screen. Okay.
We see it.
Can you see it?
Yes.
Good. All right, well, this is me. I'm from a little place called Bradley University in Peoria, Illinois. It's a long story, but I'm actually part of the Department of Physics and the Department of Mechanical Engineering. However, any more these days, my main affiliation that I claim is with this thing called Pickup. And it's a mouthful, the Partnership for Integration of Computation and Undergraduate Physics. And so we just shorten it and say Pickup, and that takes care of it. So, well, Bob, by the way, I'm going to start with something that's going to echo what Bob was just talking about. I think the spreadsheet is an absolutely invaluable tool for getting students into computation. And however, I think it's a lost art. There's a book, and I don't know these guys, but it was called Spreadsheet Physics. This was published in 1991, right? So this is why I say it's a lost art, because this was, people were doing this way back, and somehow with the trendiness of Python, and I scratch my head a lot to understand why the spreadsheet is not more ubiquitously used, for the very reasons that Bob just got done showing. The versatility of it, the power of the thing, it's amazing. And we somehow look down our nose at this business software, right? Bob emphasized that it has to be used correctly in a physics sense, and that was pretty good. Just to point out what I do with my intro students, by the way, and this is a terrible slide, but the reason I'm showing this is simply to point out there's two reasons I start with Excel, all right, or a spreadsheet. It's not necessarily Excel, but one is, especially in physics, from a physics perspective, we have got to get it in our heads that our students need marketable skills. The probability that one of our graduates, not every student who takes a physics, just one of our graduates will end up as a physics professor is something like 3%. All right, and so we are still trying in the physics curriculum to reproduce ourselves. And so we've got to get in our heads that marketable skills, and when you say marketable skills, especially in industry, I rub shoulders with a lot of engineers, and Excel is absolutely something they reach for on a daily basis. Moreover, I use Excel as an on-ramp to get my students into actual programming. And so that's what this slide explains, right? So I give them guided activities. We build the models in Excel, and they use it as a guide. So that's sort of my style of getting students into this. Just to echo one more thing before I get to my talk proper here, echo one thing that Bob pointed out, and I think it has to do with Brett's question. It doesn't take that much to get students into Excel. There's no better way to get students doing something than to just get them to do it. And if you raise the expectations of students and hold them to it, for the most part, they'll respond. And it really doesn't take much to get them into this, all right? So, all right, well, back to what I'm actually gonna talk about here. So let me go into slideshow mode, all right? I'm gonna start out and tell you a little bit about this pickup, right? The purpose of pickup, and this is the extent of it, you might wanna make it a little more complicated than this, but this tells what we're all about in this partnership. The purpose is to lower barriers for faculty across the country to integrate computation into their STEM courses. Now, granted, the UP in Pickup is undergraduate physics, and we started there because we were all physicists. However, we've attempted to broaden this to more broadly include all of the STEM. We're working on it. We haven't got there yet, but Pickup is sort of becoming a generic acronym now. So it's not just physics, all right, although that's where we started. We've been around, I'm not going to give a big history, we've been around in some shape or form for about 12 plus years, and after the last webinar in this series, Bob Panoff went and found this, so I'm going to show you what this link looks like. This was a visioning workshop that was put together about 12 years ago in response to trying to figure out why there's not more computation in undergraduate physics. And just to, for if you're curious, let's see, for participants here, here's a list of the participants. And this really was the start of it all. This was the very first thing that had the pickup acronym attached to it. You can see.
We're not seeing the list. We're not. You're not.
What's that?
You're not sharing the list.
Oh, you can't see that? Oh, hold on. Let me stop and then let me share it again. I think it should be, oh boy, where would that be? Here.
If you share the whole desktop, then you can go back and forth between.
Share the desktop. That's what I want to do, right?
Yeah, then you can go back and forth between each things. Yeah.
Okay. Does that do it?
Now we see your desktop.
Okay, hold on. Okay, I'm gonna try again here.
Okay.
Share desktop, right? Okay, now how's that?
Okay, we got it.
Got the list. All right. And so you can, the reason I'm showing this is just to point out, these were the original pick-uppers, I guess. And in particular, I want to indicate down here, look, Robert Panoff and Scott Lathrop here. So they're officially pick-uppers also. Going back to this, all right, can you see the?
Yep, we're on the slides.
Okay, good. Since 2015, we've been NSF funded, right? And so it's evolved over the years. And I'm going to show you a little bit of this pickup website. Okay, did that work?
You got it.
Good. Wow. I figured out how to use this thing. So this is our current pickup website, and it has a lot of stuff on it. Very, very briefly, I'm going to describe really two things. Take note of the URL, by the way. It's part of the Compadre suite of stuff, compadre.org/pickup. That's how you get to it. There's an easier way if you just simply type in gopickup.org. Pickup.org was taken, so we had to put a go in front of it. That'll get you to the same place. There's a whole bunch of stuff here. A lot of it still is under development. I want to just point out two things, and really one thing. There's this tab called Exercise Sets and a tab called Faculty Commons. Again, the reason we exist is to lower barriers to faculty integrating computational activities into the courses. And under Exercise Sets here, these are actually peer-reviewed curricular materials. So let me log in. And I'm just going to take you through a little bit real quick what this is all about. Well, actually, let me not log in. That's going to take, this will be easier, just point this out. Let's pick out one of these things here. All right. So this one, for instance, this is a just falling sphere with air resistance, right? These are actually peer-reviewed, and we've gone through and we've created an editorial process and a rubric for evaluating these things. Our goal in this is really twofold in the big picture, is to have materials which are uniformly formatted that can be perused and shopped around with for people who are looking for things. The second is to ensure high quality and have something that has been tested in classrooms. So that's the reason for the peer review. And the rubric has no, by the way, it has no reject step. So unlike an academic journal or AJP, for instance, the author can choose to drop out at any point, but we will work with the author to get this beat into a shape that we deem publishable. So that's the purpose of this peer-reviewed part. It's been a little tricky because what does it mean to peer review educational materials? So we've learned a lot as we've gone along. But just to point out what's in here. So this is a typical one. There's a quick description and a cute little picture to catch your eye. There's some metadata here that can be searched. every exercise set has learning objectives, and the learning objectives are tied with specific activities that we call exercises. And the default, if you don't have a login, and by the way, to get a login, you have to be a verified educator, because there is some solutions behind this that need to be protected, right? And so as you scroll down, you see the learning objectives tied to the exercises. Every one of these tabs then has other content in it. So there's an instructor's guide, which is the author's tips for how this has been tested and how to use it in the classroom. The theory behind what it is that's being the topic or the set of exercises, the exercises themselves, solutions, and the code for every implementation. By the way, we try to emphasize in the pickup organization there's no best or perfect or preferred way to implement this for many, many reasons. So we respect faculty and institutional preferences on this. So for instance, for this particular exercise set, this falling sphere, there's C, Fortran, GlowScript, Jupyter, Python, Mathematica, MATLAB, Spreadsheet. We even had somebody contribute a Haskell implementation, whatever that is, right? So then there's this thing called Faculty Commons. And we had people, as we've done these workshops that we've done, we've had people say, well, I'm really not interested in putting the effort in to have a published exercise set, but I would like to be able to display my educational stuff that I use and get feedback on it. And that's what the Faculty Commons is for. An editor will look at submissions and make sure that it's appropriate, but it's pretty much anything goes. You can upload anything here, right? And there's if you look at this, for instance, well, not that one. Let's go back. Orbital motion, for instance, here. You got to be logged in to see. I don't want to take time and do that. Yeah, I'll leave that to you to go explore. Point is, there's a discussion tab. Everything can be discussed right directly on these entries. Right. So we think that this has lowered barriers. The other thing I'd point out, and to go back to one of these, with a once you're logged in, there's these green buttons over here. You don't see it because I'm not logged in. But once you're logged in and you're a verified educator, with the push of a single button, you actually get downloaded all of the content you see here, all the figures, all the code, everything, solutions, in LaTeX, Markdown, Word, whatever you prefer. So it's not just another repository of stuff to use. And we really don't even tailor it to be used as is. We want faculty to take this and alter it, tailor it to your own pedagogical preferences and tastes. Right, so that is your brief intro to the pickup stuff. If you want to see more, let me go back to these slides here. For more details, Larry Engelhardt in the first series of these webinars did a very nice introduction to a lot more community and events aspects of the pickup. And so here's the link, and I think that can be found elsewhere also. So I would point you to that. Right? So that's the very quick introduction to pickup. What I'm going to do the rest of the time here is give a quick overview of why I think computation is important. And I guess the big picture would be what's listed here. How computation enhances course content in the sciences and engineering. I'm going to give it to you from a physics perspective, although everything I'm going to describe really can apply to engineering disciplines also. All right, there was a little spreadsheet thing. So these are my basic fundamental thoughts on integrating computation into undergraduate physics. I think it should be done early, often. I'm going to show you how it enhances content coverage very quickly. Actually, there's a lot we could spend a whole hour talking about this. And this is really that fourth bulleted point there is really the bottom line, in my humble opinion, is it exposes students to more, and not just more, and not just sooner, but let me emphasize the interesting part, right? And you'll see what I mean by that. And I'm just going to boldly point out, if in an introductory physics course, for instance, you're still sliding a block down an inclined plane, you are doing your students an extreme disservice. All right, we have to bring physics into the contemporary age, and computation is the way that's done. All right, so here, look at this slide here. I took this out of Halliday and Resnick. You can find the exact same thing in any basic intro textbook. And this is what's presented to a freshman or sophomore intro mechanics student. Look at all this stuff. In principle, they should be able to apply Newton's second law and come up with this. But once you start throwing this differential equation at them, and then you say, here's the solution, you have lost them. And what is the reason for this anyway? Here's another part of that same book that shows damped driven oscillations. This is it. Look at this. Look at that plot, figure 1516 there. Do you think any introductory physics student across a fruited plane will look at that and know what in the heck they're looking at? I would submit no, all right? And yet we show them this and we say, after we have had them hang a little spring on a thing and use maybe a motion detector and say, well, look, it oscillates, all right? Then we show this and say, well, this is really the cool stuff about springs. We're not so interested in springs. We're really interested in forced oscillations and resonance. And they have no idea what they're looking at. And then we maybe make them take this equation and calculate something. Well, here, and let's not go into the physics. You all know this very well. Here's for a hanging spring. And if we apply a driving force and have some kind of damping in it, this is the differential equation that has to be solved. Of course, they don't know how to do that as freshmen. So we just say, come back in 2 years and we'll sort of show you how to solve this thing. All right, well, look, you can either solve it via an analytical guess, or something as simple as the simple Euler-Kromer algorithm will work. Well, I don't want to take time and emphasize the algorithm, but this is it, all right? And let me stop this here, and I'm going to go to a spreadsheet, all right? Just to show you how this works, and it doesn't have to be any more complicated than Excel, very much in the spirit that Bob just showed. And look, these are damped oscillations, and you might look at this and say, well, Prof. Roos, this is a terrible scale you're using. Well, I'm doing this on purpose. I've got a slider bar here for the driving frequency, and look what happens. And if you have students build this and just start playing with the driving frequency, by the way, I have a K of 25, M is 1, so the resonant frequency is about 5 here. And so as we approach it, look, we're maximizing the amplitude in the system. Resonance pops out naturally at them, and they don't do any integral continuum level calculus to come up with this. Freshman physics students can do this and start to appreciate the concept of resonance. All right, here's another one. Let me move on to another one of these little things. Rocket motion. Here's the typical thing we show students, freshman students, and you throw this at them and they're already afraid of calculus. They're already freaked out in integrals. Here's another part of this, Halliday and Resnick. Look at this, finding the velocity. This is freak out time for freshman physics students, right? Here's what I do, right? And I really do this with freshman students. We take the impulse momentum theorem, make a few approximations, and you come up with this, which, by the way, you know, this is the external force term here. This allows students to understand what thrust is. It's basically delta M, the exhaust, delta M over delta T, the product of that with the exhaust velocity. So already you're getting into real physical concepts that are more than just than this esoteric rocket equation you throw at them, right? And so what can you do? Here's the differential equation that has to be solved, which, by the way, I wouldn't really personally want to try to attack that analytically. I'm not even sure how I would go about it. I don't remember much of my calculus, but look, Euler-Kromer actually nails this with a few simple iterative equations. And so you can find the Saturn V flight plan online. And what I want to point to you real quick is just this, see this red line here? See that? It's the red line. Let's just look at this first part. From here to here, this is the first stage, right? And I have my students implement this, and in particular, look, there's this little double peaked thing in the acceleration. I actually have them do this, and you can do this in a spreadsheet. right? And look, you can actually nail the launch of a Saturn V rocket. These are the 3 stages. First one here is where you jettison the fuel tank and you ignite. The second one here, jettison the second stage, and then you're off and running with the third one. So these are interesting, and they get students not only into dynamics you would never think about getting them into, but it's really cool. I have had to literally kick some of my freshman students in the butt and tell them to do their analytical problems because they start playing with this and they get lost in it. And they actually enjoy it, believe it or not, right? So I'm going to, I have a lot more stuff, but I'm not going to do it. I will make the slides available, and I think probably you're going to post these somewhere.
Yeah, I'll post it along with the video. So
yeah. And so one last thing to leave you with, and I didn't. This will be like 2 minutes, and then I will stop. In advanced, I didn't talk about advanced courses, but I think that in advanced courses, physics or engineering, we have to get discretization in the curriculum. That allows us to solve PDEs and allows you to interact with not only the Schrodinger equation, but other things of engineering interest, like the heat equation and diffusion equation. And let's just take the Schrodinger equation as an example. And let me just show you one of these real quick. It doesn't matter. This is the classical scattering problem. And let's do it with a, let's do this one, I think. Can you all see that? You're watching a particle approach a potential energy barrier, right? And it gets reflected. Let's do another one where the energy is a little different here. So this, of course, is a quantum mechanics class, so this is an intro, but the advanced is the same thing. You could have them study. Now, here's the transmitted part. Here's the reflected part. You could have students do this via the old traditional route of using stationary states, which are not normalizable, and using an inherently time-independent approach to try to get them to understand a time-dependent problem, which sounds rather insane to me. Or you could do a simple discretization, which doesn't require any more mathematical preparation than a Taylor series and a little bit of partial differential equations, or not differential, partial derivatives. And you could have them doing that, those types of dynamics I just showed you for scattering. All right, well, that's that. I'll stop there, even though there's more slides and you'll be able to see the other stuff up there.
All right, thank you, Kelly. So are there, first of all, Scott posted to the chat window that if you're interested in keeping touch, if you want to put your email address in the chat window, we'll save that and inform you of the links to all of this once it gets posted. But you can either, again, unmute to ask Kelly questions or put something in the chat window. And so we'll open up for general questions for Kelly, or if things that occurred to you relative to Bob's presentation, go ahead, please.
So this is Bob. I just wanted to talk about another kind of non-programming use of computing, and that is there's a number of tools that don't have to be programmed but can be used rather directly. One of which we've developed here at Shodor is called the multifunction data flyer. And I was reminded of this when Kelly was showing the oscillating things were on in Halliday and Resnick, or in some book you have some equation and you're saying to yourself, how am I ever going to make sense of this? And so one of the things that we've been doing is developing the ability of looking at some of these things. This is the multifunction data flyer, and I've typed in that equation that Kelly had, or something very much like it. And then the question is, if you see that equation, and then you say, what does it actually do? Well, if I change the first variable, it's changing the amplitude. The second one is changing the frequency. The third one is changing the phase. And the fourth one is changing the bias. But the idea of having a tool like this, which is free, it's accessible, anybody can use it. I'll put a link to this in the chat window. But the ability of typing in any function that you want to have, you know, this understanding of what is it actually doing and why does this equation seem to be helpful and what is it really describing. You can also use it to fit data, but that's another feature. But just to show you that those things are out there, and the computation is what enhanced the understanding. It doesn't necessarily get enhanced by programming yet.
Right.
But I've had students that have used this in a lot of other classes. You know, I've had the dean of the School of Engineering say, where was this when I was learning, you know, various equations? I'm reminded of Peter Fetters at Washington University, who used to scream at us, there's nothing special about special functions. You know, they're all written down, they're in a book, you type them in, you learn how to use them, and you pick the one that looks like your data, right? And that's one of the things that students don't have, is a good sense of what do these functions actually look like. So anyway, those things are available. And I'll post the link to that.
I wonder, Kelly, if you could, I know you've implied that this really helps your students sort of visualize these complicated things. Have you done any sort of assessments that show that this helps the students get through this material and understand what's going on better?
Good question. This is one of the, this is the trick, assessing, you know, computation and what we want them to understand is such a different approach than what we traditionally have used that it's difficult. It's a difficult thing to do. All I have is personally anecdotally observed how they've responded. I haven't done anything like a physics education research level study or anything like that. However, that's something that the greater pickup group is starting to attack now, right? So, but just anecdotally from my observations, students actually enjoy doing this stuff. That's you sometimes hear squeals of delight when they have built their model and they actually realize it works, and they can change parameters, and not just change. You know, Bob showed the function. I think that's a fabulous tool, but actually changing the computational algorithm itself, and understanding why it works, and taking control of that aspect of it gives them such a sense that they've accomplished something, far more than those typical end of chapter physics problems where they come up with an answer, a numerical answer, circle it to never ever revisit it again after they've matched the answer with the back of the book, right? So it gives them a sense of ownership, power, that they have actually achieved something. So I observe this all the time. Not everybody. I mean, we all have our challenging students, right?
Yeah.
But for the most part, they all really far more enjoy physics more than my students in the old days when I was a talking head and made them do a lot of end of chapter problems.
Excellent.
I guess the related question to that is, are the students able to learn more in your normal class than they otherwise would have?
That's a good point. A really very good question. Again, if we go back and think, what are we trying to assess? So this all comes back, and this is why in the pickup we have learning objectives tied with our activities, all right? If you ask, what do we want our students to be able to do? If we want them to be able to derive some physical equation based on a principle, then I would say probably the computational route isn't the best way to go in the traditional learning sense of what we think traditional physics is. So along with computation, I'm suggesting that we don't just get computational activities in just to reinforce things. I'm suggesting this has to be a revolution in the way we do science education. And so, for instance, go take my quantum mechanics example. Do we want students to be able to just analytically have a way to understand that there's such a thing as a transmission and a reflection coefficient? If that's the case, the old approach, formalism, although not correct because these wave functions are not normalizable, it really is a trick to get around the fact that the analytical solution is too hard to do. You can't do it, right? Or do we want them to be able to actually understand and interact with the postulates of quantum mechanics in a way that they can build a model which demonstrates not only the solution to an equation, but the actual physical ideas themselves, all right? And so that's what I meant by, are we trying to turn our students into ourselves, or do we want them to be able to build models and understand what's happening? So Scott, the question has to be, what do we want to assess? Not so much, is it improving on learning in general? It's what we want them to do, which has to be the focus, and then we can build assessments based on that. And that's coming, by the way. There's not much been done yet, believe it or not, on broad effectiveness of computation. It's coming.
The simple introductory tools that we've been using to kind of get people going. There's an educator here in North Carolina who likes to say that the trouble with our students is they don't know what to do when they don't know what to do. And what we're finding is that after a few examples where they're using computation, the what you have equals what you had, plus what changed paradigm, is that they can take a problem and sit down and write down what do they know, how do they put it into a simple form, and then iterate. And they can actually do a number of problems that they couldn't otherwise do. Like, what do you get when you add a restorative force like a spring? You know, why does it spring, and how big of a change does a small change in that parameter make? You know, how big of a change is the damping at? You know, what's a large number? And those are all things that they actually can play with in a scientific way, because they can ask and answer questions of themselves, and it seems to capture their attention and then keep them going.
Mm-hmm.
All right, are there other questions? Well, if not, we've gotten to the top of the hour, so I would like to again thank our speakers, Bob and Kelly. And as I said earlier, this will be posted in a few days, along with links to the presentations. And a number of you put your addresses in the chat window, and I've saved that, so we'll directly send you a note when everything's posted with the links. So thank you again, gentlemen, for your presentations, and we very much appreciate it. And wish everyone a good rest of the day, and we'll call it a day here.